Because this paper is not for you. It's for somebody. I always do things that is fucking hard to understand, but reasonable in the end. You will understand it.
It's really a pleasure to have Michael Berry talk again. He has already talked, I think, twice before in this webinar, and
important is the local phase gradient. You can think of this as the local wave vector. It's curl-free because it's the gradient of something. The little wave vector. And, well, for the Helmholtz equation in free space is literature in engineering in the 20s. Atom party, land side, on side. Vanishing quantity. And there's a great deal of interest in mathematics that comes, which we're exploring and trying to turn it into sensible physics to see where the curliness of the force affects the quantum solution in the cases where we do have a Hamiltonian. Very unusual wave equations and parabolic cylinder functions based on a complex game we never really get over there. It's a long story. But more than that, what we really would like, which we haven't yet achieved, is to find a curve which isn't one of the types where you can find
was told that tomorrow is Michael's birthday. Is that correct, Michael?
So I'm told.
You are told. Well, happy birthday, Michael.
Well,
very happy birthday.
Need not be closed. Closed. Don't be accepted. Philosophy, rather than economic. Good. So just to show you an example, here are three plane waves, lots of singularities. You've got the canonical streamlines, you have the phase singularities, and you have the vortices. You have the saddle points, and circulating around one, hyperbolic around the other. And with the V, it's the exact opposite. And this arrow here represents the mean kinetic velocity. And it sort of, you see this vaguely a general direction of flowing upwards and to the right. In momentum space, history and it goes faster and faster around. Good. I'll show you the classical orbits. We found them some years in the fields of Cup. Now, I wasn't really aware of what you said. But it isn't surprising, it sort of has to do so, doesn't it? Yeah. Yeah, thank you very much for that.
Are there any other questions or comments?
There's an old, which is the part of what, Chris, the three parts of the talk are in the title, that's the summary. Chaos, well, we heard about it already.
It's an honor to have Professor Michael Berry from Bristol University today. So Michael, for this about chaos from the efficiency of the
Thank you. Pleasure to be part of this meeting. Thank you, Joe, for organising it. The three parts of the talk are in the title, that's the summary. Chaos, well, we heard about it already this morning. It's rather small in every chaos itself. Chaology, if you look in the Big Oxford Dictionary, with rare words, they list the number of times that they've found occurrences of those words, like rare 3. Well, chaology is rare 0. And I asked the creator of the online version of the Oxford English Dictionary what that means, and it means he only found it in earlier dictionaries. Okay. Now, there's a new fundamental constant, of course, Planck's constant, usually written like this. It's rather small in everyday units. The units are units of angular momentum, 10 to the minus, 10 to the minus, I have to put it there, 10 to the minus 30-something, sorry, very tiny. Now, we have correspondence principle. Quantum mechanics must reduce to classical mechanics in the limit when Planck's constant is negligible. 0, we call it, negligible compared to other quantities of the same type. Well, that's correct, but it conceals a lot more than it reveals, for a reason which is my central point. I'll get to it. It's an example of something more general, how different levels of description are related to each other. Statistical mechanics of matter reduces to thermodynamics in the limit of many, that's the particle number. Philip Anderson beautifully wrote about this. More is different. All kinds of difficulties arise with that limit. In fluids, viscous flow reduces to slippery flow as the viscosity goes to 0. Many problems still not understood about that. It involves turbulence. In light, wave optics reduces to ray optics as the wavelength goes to 0. And of course we have this example of quantum mechanics. Now, there are two ways of thinking about this difficulty of taking limits, and they're both oversimplified. One is, are these incompatible descriptions? I'm adapting a phrase of Stephen J. Gould. Are they non-overlapping magisteria, not to be mixed? Or, in a beautiful Old English word used by E.O. Wilson, should we seek consilience between these different levels? Now, I'm more sympathetic with the second, but they both have their place. Now, common to these correspondences is that they involve mathematical limits. Now, in almost every case, discordance is associated with the fact that these limits are mathematically singular. So fundamental mathematical phenomenon central to this understanding of differences between levels. Now, a singular limit needs explanation, and I'm going to give you a very simple example. Bite into an apple. If you see a maggot, you're unhappy. If you see half a maggot, you're even more unhappy. A quarter of a maggot, more unhappy still. Take the limit. If you see no maggot at all, you should be infinitely unhappy. But of course you're not. It's a singular limit. The limit of smaller and smaller maggot fractions, infinite unhappiness, is different, discordant with the limit of no maggot at all, you're happy, you continue eating the apple. So common language, simple example of a singular unit. Now, this perspective enables two insights which are qualitatively different. One is reassurance, to show that the old theory emerges from the deeper one, usually not straightforwardly, but you know it must happen. When you program a spacecraft to go to the moon, you don't write the Schrödinger equation and treat the spacecraft as a wave packet. Of course you don't need to do that. But you know that in some sense you will regain classicality, not trivial. And the other is there's a creative aspect, because it leads you to identify qualitatively new phenomena inhabiting the borderlands between the two levels. Now let's look at the reassurance, quantum to classical. The simplest possible case, take two oppositely directed beams of particles or beams of light. Here they are. Now, when they overlap, the intensity is doubled. Two flashlights are twice as bright as one. The mathematics is 1 plus 1 equals 2. You may know that formula. Now, but of course, if you have waves, which deep down you know that you do have them, that's different. The intensity is the square of an interference amplitude. 1 plus 1 is not equal to 2. The intensity will be anything between 0 and 4. Now, the limit is when the wavelength goes to 0. It's the same in quantum mechanics. So the oscillation gets faster and faster as it goes to 0, and the limit is very singular, anything between 0 and 4. Well, you know that beyond a certain point, the wavelength is too small to resolve, or the delicate coherence leading to this nice pattern is destroyed by external influences, and you see only the average. So the average is in fact 2. So, 1 plus 1 equals 2 is restored by something called decoherence. Now, I'm not being pretentious when I say that 1 plus 1 is not equal to 2. As pure mathematics, it's of course a very simple formula. Even though, if you know Russell and Whitehead's Principia Mathematica, 1 plus 1 equals 2 appears only halfway through volume 2 as the first non-trivial example of their mathematics. Still, it's as pure mathematics, simple. But this is applied mathematics, and you have to understand with any piece of mathematics, if you want to talk about it in connection with the world, whether it actually corresponds. You know, two people get together, produce a child. 1 plus 1 equals 3. Two raindrops going down the windscreen of your car and coalesce. 1 plus 1 equals 1. You have to know when it applies. It doesn't apply to wave intensities unless you introduce something external like decoherence. But still, you have reassurance. Now this sensitivity to decoherence becomes more and more exquisite if you approach the classical limit in a case where there's classical chaos. And here's an example. Saturn's satellite Hyperion. It's a few hundred kilometers across. It's potato-shaped rock. It tumbles chaotically under the influence of the gravity of Saturn and some of its satellites. It's roughly a period of about 13 days. Its uncertainty doubling time is about 100 days. Now, think of this as a quantum object. It has a quantum rotator, about 10 to the 60 planks in its angular momentum. Okay? And if it were isolated, any uncertainty would grow and get increasingly complicated in the relevant space until it reaches a scale of Planck's constant, and then quantum mechanics can't see it anymore. And that's after that, Hyperion would reveal its quantum nature And the way it would happen, so I don't have time to explain it, but the energy driven by these external will determine gravity from satellites and Saturn would no longer increase. That has a name. It's called the quantum suppression of classical chaos. It's seen in molecular experiments. It really exists. Well, when would that happen? Well, after about 40 years. Remarkably short time because of this chaos and uncertainty. And it's obviously nonsense. You don't look at Hyperion for 40 years and see its chaos suddenly stop or even gradually stop. The reason, of course, is that this suppression of chaos is an effect of extreme coherence requiring strict isolation. Of course, it isn't isolated. A single visible photon from the sun, whose re-emission enabled us to see it, has an energy of about 10 to the minus 19 joules. That's tiny compared to Hyperion's rotation energy, which is about 10 to the plus 19 joules, but it's huge compared to the energy separation of the energy levels of these different angular momentum quanta in Hyperion, which is about 10 to the minus 39 joules. Well, that means that the stream of photons from the sun, their uncontrolled external influence, completely destroys the quantum coherence in about 10 to the minus 53 seconds. Okay, so decoherence. Now, first of all,
great pleasure to have Michael Berry again talking at us.
And one of them was by a retired physics teacher, John Tarrant. You get this linear superposition. Try to combine is where you would see. I don't think so. Now, you would mean quantum optics. You mean, would there be any interesting, for example, photon counting statistics or something of that? Is that what you have in mind?
And basically, the interference phenomena of a more subtle character.
But, I mean, this is so back in geometrical optics, so to speak, and the cut. And here's what we need. Now look, it's in X. And then the ray intensity is the reciprocal of this Jacobian. It's a thing that diverges.
我去，这也太神奇了。Those new physics. Because it sounds good. That sounds. I know, but I'm in China. I'm in China. I have to. It sounds like. Yeah, like. This is indignity for female. Even 10 years can quickly lapse quickly. Even 10 years can elapse quickly. I can't put up with your hypocrisy anymore. We were cheated by his hypocrisy. This is a mere assumption, resting on no facts. This is a mere assumption, resting on no facts. These actions were based on a false assumption. The facts were proved that her assumption was wrong. Proved that her assumption was wrong. Mushroomed of the past decades. Don't eat the pointless mushroom like mushroom soup. The country was in ferment. Porpoise looks like a large grey fish. Large grey fish. Porpoise usually swims about in groups. Tom has a son for girls. Tom has a charm for girls, fascination for girls, listen of science. Of science. The kingdom of science, the realm of science. I hate to squabble with my wife about money. The longitudinal line. I found the wreck of an old ship. I cannot be held guilty, culpable for the mistakes. I cannot be held culpable for the mistakes. The judge found me culpable. The country was in ferment. Tom has a fascination for girls. The country was in ferment. Tom has a fascination for girls. pen holder. The pen holder is made of bamboo. The pen holder is made of bamboo. The pen holder is made of bamboo. There is a pen holder on the desk. I want to make a pen holder with this bamboo. This pen holder is made of bamboo. There is a pen holder on the desk. I want to make a pen holder with this bamboo. Drum. We hear the beat of drum. Potency. Potency. Potency of medicine. Alcohol increases the drug's potency. Cell potency. Potential. Potency. Discrediment. What is that? Discrediment. There was good reason to discredit the witness. There was a good reason to discredit the witness. There was good credit to There was a good reason to discredit the witness. He brought discredit on the whole family. They made an effort to discredit the politician. Discredit the witness. He brought discredit on the whole family. He made an effort to discredit the politician. Discredit. Brought discredit on the whole family. Discredit. Demon. He's a demon at chess. His husband is a demon for work. The demon let out a horrible roar. Mortgage. We'll have to mortgage his land for a loan. Potency. There was good reason to disgrace the witness, discredit the witness. We will have to his land for a loan. Mortgage. Potency. Discredit. Mortgage. We will have to mortgage his land for a loan. Mortgage rate decline.